All right, everybody. So I have a kind of extended intro to explain why I'm up here, but so my good friends Gedalia and Aaron weren't able to make it due to different various circumstances. And I'm friends with both these guys, and I kind of know what they're working on. So I'm Don, and I'll introduce myself a little bit. Why I feel like maybe I have probably just a little bit of authority to talk about what they wanted to talk about, and then give you the slides. So Gedalia and Aaron work for a company called KOVERSE, which is building a data platform that has some unique things about how they aggregate data and do data discovery things, and are building this platform in order to kind of enable data-driven applications in large institutions, mostly commercial. And my name is Don Miner, so I'm going to be presenting their slides. And I run a services company that mostly focuses on building data platforms, cloud systems, and machine learning applications for various commercial entities like railways, clothing companies, whatever. And actually, one of the projects that is discussed in this slide deck is one of the ones that we help them work on as well. So us and KOVERSE have like a relationship where we work together. So with that, this isn't necessarily my talk. I think I'm going to be prepared to answer some questions about it through my intuition, but I may defer you to ask over email or something like that. All right. So wish me luck. This is the first time I've ever seen these slides. No, I'm kidding. I've had an hour to prepare. I've had a little bit more than that. I'll start with one of my favorite stories in Las Vegas. One time I was working for a company called EMC that you may know about, and there was an 8 a.m. talk that a friend of mine was supposed to give, and me and my other friend went to go give him support, and he was pretty bent out of shape from the night before, from what I understood, and he never showed up, and my buddy gave the talk without ever seeing the slides before, and that was pretty funny, but this isn't that bad, so. All right, let's get started. So, just in general, the talk is mostly spread up into 2 sections. So we're going to talk a little bit about how Accumulo is used in these use cases, and the particular table structure that is used behind the scenes in KOVERSE. And then we're going to give 3 examples of how that was used in industry. And the overall theme here is the diverse set of machine learning applications that generally people want to be doing, and some of the I guess the major point of this talk is, what are some of the underlying things that KOVERSE has been doing on how to organize the data in a way that's appropriate for machine learning applications, both on training and on application of the models. So we're not going to go into like the actual machine learning stuff. It's mostly just a talk on how Accumulo underneath is used to host these applications out and some of the interesting things they did. And really using table design patterns that have been used in the past, just making more sense here. The other thing too that's really interesting is the access patterns are pretty diverse in how Accumulo is being used in these applications, so we kind of have to design the thing to be both flexible and performant. And then finally, over the course of a few different use cases and probably a couple other ones that aren't discussed here, there were some like kind of guiding principles that was true in general across a few of these. Which is kind of like the main contribution of here, of what we're talking about. All right, so summary, we are talking about machine learning on Accumulo and kind of what table structure that particularly worked in that case. So the main thing is split up into 2 sections. There's like the actual record table, then there's this index table, and I will go into that. So basically each record is going to be stored as a unique record ID. So every piece of record, like it rained today, or this person has diabetes or something like that, is going to be a separate record, okay? One thing that they particularly wanted to optimize for was being able to read new records that have come in time, meaning new. So if you have a machine learning model that's, let's say, extracting some information from a document or applying some sort of inference to a thing, we only want to run that over new data because that's the data that's useful, and also too, it's the data that we haven't classified yet or extracted from yet. So one of the big pieces of the optimization is we want to be able to read from particularly new data. the one kind of intuition here, if anybody's gotten this deep on Accumulo layouts, is if your key is a timestamp, right? What happens is that the data gets added to the end of the table always, or the beginning, depending on how you laid it out. So one tablet will get hammered with the new data. So one of the ways that you get around this is that you prepend this like arbitrary bucket ID to the beginning of the key, which then splits up the new data over multiple tablets. And so that is one of the primary things that we're doing here. And one of the downsides of this business is that it makes it a little bit harder to find the record because there's an arbitrary bucket ID on the front of it. So what they also did, another access pattern that you may want to do as well is to search for certain attributes of the data, which would be in the value. So we need to create an inverted index that's going to be looking into this thing as well. That's also going to keep track of the buckets. So the table schema I'm about to show you is basically doing that. So the record ID in the schema has this bucket ID, which may have a various number of buckets. I don't think there's a science about how many buckets we have, but it should be like close to the number of tablet servers, I think, or tablets rather. Maybe more, maybe less. Maybe it's determined based on how large the data set is, whatever. And the other thing to really point out here, which I think is really key on why I think Accumulo is an interesting data store for machine learning, is the fact that the different data sets, doing machine learning over multiple data sets is pretty hard overall. So when we're talking about storing lots of different data sets, like 7, 10, 15 data sets, in order to create this this one machine learning model that pulls from all those data sets, having them all be in Accumulo is pretty nice. So in the way that we're storing data in Accumulo for these use cases is we have this arbitrary bucket ID, then we have the data set ID, and the reason why we have that is so that we can store multiple different data sets in the same Accumulo table. And then we have the timestamp for that individual data source. So the nice thing is that inside of each bucket, which is the beginning of the key, we have all the data sets that we have, in this case, data set A, data set B, and we have maybe other data sets in here as well. And then inside of those buckets, they're time ordered. So if you add new data to the data set, we probably collect data set together, data set A together, separately from data set B. And so data set A will be written into bucket 0 and 1 kind of in parallel. And that data is added to the ends of those buckets. So you don't get the problem of that all the data is hitting one tablet. It's spread out across the different buckets. And then the other thing that and I think that's important for the temporal, like only applying stuff over the most recent data. It's really useful for that. And also too, from writing perspective, I'm not sure on this one if they're doing any bulk loading or they're just doing just regular writes or not. That's not something I'm sure of, but I could imagine a scenario where you could do some bulk ingest here. The next one is that this supports pretty good reads on when you want to read from new data. So when I'm reading from new data for a data set A, let's say, I can say give me all the new data from data set A because I'm going to hit every single of the buckets. I know how many buckets I have. So if I have 200 buckets, I know that I need to have my batch scanner hit all 200 buckets. I'm going to pull all the data back. And then if I need to do any sort of consolidation, I can do that in the client. But performance-wise, this is not unreasonable in comparison to just having one massive batch scanner. All right. And also, too, this is nice because it pulls the data set from spread out across the Accumulo cluster. So you're removing this is also another issue on read if you prepend all the data at the end of your table, because then when you're reading the most recent 5 minutes of data or 2 days of data, it's all pulling off the end of the table, which is only going to be hitting 1 or 2 tablets. So this also spreads out the reads for batch processing. With machine learning on training, for example, or if you're trying to do summary on some sort of recent situation to do some inference on it, this is a pretty common access pattern. We're not fetching individual records. It's I want to know all that happened in the past 5 minutes, and maybe I want to make some inference on some forecasting or something like that. All right. So this separate index table is basically an inverted index onto that thing where we are going to set up the table so that we can query on the things that we want to query on and get back where those records are, and then we can go fetch those records. So this is going to support the the point queries. So, I want one individual record. Or if I want to search on certain fields, then I can get back like, hey, all the fields that have this property, what is the record ID for the things that I need to go fetch? Because once I've obfuscated like this with this record ID dataset business, it's really hard to work backwards on that sometimes. In some cases that if we want to do any sort of like set intersection, like we want to have this record and this record, or the records that have this feature and the records in this feature, we would do that intersection on the client side in this case, since they're just point queries. And so some context here is that some of this stuff is being accessed by applications instead of just machine learning processes. So there may be some dashboard somewhere, or web application, or in one case, like a mobile device that's going to be hitting this thing in real time. So this is kind of like what it looks like. I think this is pretty common in terms of approach for an inverted index. I put my, in this case, I have the data set ID on the left. I have the field in particular that I want to be indexing on. And then there's some other kind of things like the value in the record. And we also have the ID and the value to say like where this thing actually is. So what this kind of allows us to do is ask questions like, where people are between a certain age and it contains Bob in some way. We can kind of scan this index table, which is a little bit smaller, obviously, than a larger table. We can figure out what records we need to go visit, and we're going to go visit those records and be able to pull them back in a point query fashion, right? All right. Okay. So when basically one of the downsides of doing the scheme is that with an index table, but it's pretty much the only way to do it, is we're going to query this index table, and we're going to get back the record IDs, and then we have to go back and batch scan those things that that came back. So it's kind of like a two-hop kind of thing. All right. Hold on a second. Let me read this slide first. Okay, so in composite keys, if I have two keys that I want to search on, the problem that I have is that I can only really search on the first one. The second one is going to be unordered. So the one way you get around this is you create a composite key where you actually take the two values and you interleave the bits. And there's a few different schemes for doing that. And then you have this new composite key, which is on the right here, on the left side, which is now doesn't really have that much meaning overall. But in this case, for example, for the case of example, you can see that we're doing age and height. So on age, you have 1, and then on height, you have 6. And then you have 4 on age, and then you have a 7. So you get 1, 6, 4, 7. So what we did was we interleaved the bits, and you're about to see how this works out. And you can do this in multiple dimensions as well. And then that now points to the record ID. And then you get this pretty thing, which is, at the end of the day, if you iterate through if you draw the age and height, the linear order of that interleaving looks like this, which is like kind of pretty. What is this called again? It's called like a Z-order or something? Z-order curve, yeah. So in particular, we've seen this used with lat longs for like geo stuff. This is where I've seen it a lot, but you can use it for any arbitrary two-dimensional thing. And the thing that happens is that if I search for age less than 30, or greater than 30, less than 50, and height greater than 50 and less than 70, you get this bounding box around it. And there are some false positives, or there's some true positives, and then there's the false positives which are outside of the box. But the problem is that you have you have negatives that are inside of the box. So you are guaranteed that all the true positives are inside of the box, okay? But you have some extra stuff that you need to prune out in the client. So the basic idea here is that, if I know that I'm going to be querying on age and height in my machine learning thing application, that I can basically query for those records relatively quickly. The one thing I'd like to point out though is that these composite indexes need to be created ahead of time, right? With some thought on what you're going to be querying on. So I can't, like, if I want a composite index on height and age, and then I want to do like height, age, and gender, now I need like a new composite. I need a composite index for every single category, effectively. there's some other tricks. Like I could just say like if male is 0 and female is 1, then I could like just say greater than equal to 0, less than or equal to 1, but you lose some performance out on that. But it's a pretty powerful scheme that's used in a lot of different places. All right. So are there any questions about, that's my last slide on the actually, I'll summarize what I said. So basically, we have a Accumulo table that we care about time ordering, so we're going to bucket it. And then we have an index table that looks into that thing. And if we want to do indexing over multiple values, we can use composite indexing. Okay. Now, I'll add a little bit of my personal flavor here. Maybe one of the other speakers would have done this too. Is that, okay, so let's tie it into machine learning. Like so what? Machine learning likes the data, so I care about time ordering in machine learning because I want to apply my machine learning stuff to the newest data that's there. I also want to be running over multiple different data sets without pulling from multiple different places. And I want to have things like relatively grouped together so I can apply these things together. I need to have a batch access pattern like the buckets provide me. And I also need to do point queries so I can look at that data for an application. And this kind of provides all those things. Like if when I'm using a SQL database, for example, for this type of application, there's not really a good way to do like temporal ordering, for example. I mean, there's partitioning, but even that's like kind of wonky. So we really did find that there's not very many things out there that can really provide this sort of thing. The other thing too, comes up in one of the use cases that we're going to talk about is on visibility labels is actually somewhat relevant in this case, where we may want models that only are trained on certain aspects of the data, such that we don't one kind of area study recently is reverse engineering models and figuring out like what that data was trained on. And so if you can be pretty, more confident than you were before that the visibility hid some things from you on the model training. All right. Any questions so far? This would be a good time to ask any technical questions before I get into the use cases. Yeah. All right. Alex, can you keep track of my time? All right. I don't know when I'm supposed to stop, so. All right. So anyways, one thing that PwC does is evaluates risk in their supply chain. So they want to be aware of like things that are happening in the world that is going to let them know that some bad things are about to happen before they happen. And they have some examples are vendors with like unethical business practices could be risky. You could have a country that is becoming risky. You can have a history of tainted products and things. So there's all this information out there on the internet about companies, and it's a lot to sift through. And also too, there's new situations like, for example, some sort of strange new event could have happened in a country to make it all of a sudden unstable. And so now your view of that company is now different because of this future event, even if you have all this older data on that individual. And until now, PwC was very manual, and they were evaluating each vendor every a couple of years. So you can see like if something bad happened in a particular company, or even things like the impact of like Brexit, for example, or any sort of like policy change. They're pretty far out of date, and it exposes them to a lot of risk. So they wanted to add some capabilities in order to be able to make these kind of inferences as they were coming in, opposed to kind of every 2 years. And also to scale it more so that we can be paying attention to the companies that maybe were lower risk that we just didn't care about, and look at more things overall. So they went from evaluating every 2 years to evaluating each vendor's risk every couple days. And there's also the inference of the supply chain itself. So if you have vendors of vendors of vendors, maybe one vendor is not particularly risky, but we know that one vendor is providing another vendor, which then that risk kind of like carries on past that one vendor. And so this is a pretty like tricky use case because it's multi-levels. You have to figure out which vendors are related. You need to figure out which ones are risky. And so the way this was done was a bunch of social media data that was being published about these companies, and was one of the first things that we did, was pulling the, I think it was mostly Twitter, and there were some other feeds, like some news feeds as well, for doing machine learning on that stuff to evaluate risk effectively from those sources. So there's language that's associated with risk, and that was translated into these inferences that were made on a daily basis. So some of the features that were used here, one thing was that the one thing that was really nice was that the different data sets are very diverse, especially when at a company like PwC, like that is huge and has built on business practices that they've been using for decades. Like there's going to be Excel files that are coming through. There's like database dumps. There's calls to web services. There's feeds from social network sites. And so Accumulo provides this like sink that allows you to send all your data to. Your different data ingest processes are a little bit different in each place, but for the most part, at the end of the day, it ends up in this one kind of universal reverse index, like indexing bucket scheme that we talked about earlier, which is really powerful because I don't have to worry about necessarily exactly how I'm going to organize this data. And if I build all my applications, this is an important thing too, is if I build all my applications to run off this data source, then when I add it in a new data source, I can fold it into my model a little bit easier than I could before. So, and they were running these incremental batch processes to refresh the results on their risk scores for these individuals on a daily basis. All right, the next one is a cyber monitoring use case. So they have a company that had pulling in, so they care about threat monitoring, detecting issues, and then providing some sort of mitigation strategy to an issue. And so before, this company had been using Postgres to store all this data, which we can imagine would, I mean, I can't even imagine that they actually tried that. And so, you know, at the end of the day, Accumulo is obviously more scalable, and a foundation helped them do that. And also, too, they ran into some issues with like multi-tenancy and having different people having different access to things. So that's where some of the visibility label stuff came into this customer. And the cyber logs in general are like, there's lots of them, and they all stream in, and they're all pretty big. So Accumulo, from an ingest perspective, of being able to pull in all the cyber logs from like, I mean, dozens of different sources, all into one table scheme that we're running our models on, was pretty powerful. The other thing too is that they were able to do, one thing that's really important with cyber in general is being able to do this like threat detection over a bulk set of events. So, you know, if you look at any one individual cyber event, like an SSH login or like a proxy request, it doesn't give you a lot of information a lot of times. And also too, these events happen in short time sometimes. So like you may want to be looking at a window of like 5 to 10 minutes to determine if there's some sort of event going on. And so this supported some sort of batch analytics on the on time window data. They had a lot of indexes on this data. So like threat signatures sometimes appear in multiple different sources and over different spans. So they had lots of different composite indexes that were searching into this thing in different ways. All right. This one's pretty interesting. So this one, basically, they have a company that has a bunch of documents about individuals. So like very free-form documents. Some of these were coming from personal laptops, databases, email attachments, shared drive, SharePoint. They were coming in from different like sorts of places, and they basically needed to run OCR over these documents and provide and index these documents in a way that is searchable. And so it's basically a big searchable application. And a lot of the users had need the ability to be able to access this data from different mobile devices. So that's where the, so basically that search use case really heavily is going to leverage the index table and allow them to pull these documents back really quickly and the results of the NLP extraction. And so they did a bunch of NLP stuff on the raw document records and stored that in there as well. And we're able to apply those analytics on the things in relative good performance due to the bucketing scheme. And also too, this data was so sticky and so many different styles of data that again, kind of this common theme of being able to store all my data in one big table was really powerful as well. So, all right, those are the 3 examples I got. Does anybody have any questions? Yeah.
How are the indices maintained? What are the life of the data?
This is a great question. So in a reverse index scheme, oh, yes. The question was, how are the indices maintained over time? And the issue with, okay, so there's one big issue, is that when I write records, it's not guaranteed, you can't, there's no semantics for me to guarantee that the index is updated in kind of a atomic way. So what that means is that there is a race condition in which the data is in the bucket, but not in the index. And there's plenty of Accumulo experts in the thing, so please don't be scared to correct me. But I believe that the typical thing we want to do is we want to update the bucket first, and then update the index so that there's no like loose index thing hanging. But other than that, that's one thing you have to be careful of, that data, just because it's written to Accumulo, isn't necessarily in the index yet. And then, so the indexes then need to be, as you're writing in the data, after it's done writing, I would go in and update the index manually, effectively. But we don't do that at the same time, typically. I don't know exactly what they did in this case, but I'm going to assume that's what they did. Yeah. And also, too, kind of on updating the indexes in the sense, this probably isn't your question, but I think it's interesting to note, is that the composite indexes, these can be created in batch on the side. So if you decided you wanted a new composite index or you wanted to index in a different way, you could go back and just recreate the index in a batch fashion or create a new one. So does anybody that's building machine learning applications on top of Accumulo here that feels that there's something special about Accumulo that makes their job easier? His answer was that one of the things he likes about Accumulo is that he's able to clone the tables and go back and basically revert back to an old table. Like, why do you think that's interesting for machine learning in particular? Yeah. Okay, so like versioning of the data in general is nice in case you ever wanted to revert back to some older state. Yeah, that makes sense. Yeah, that's good. Any other answers? Well, I have one. So mine is that when you have entities that you're trying to do some sort of inference on, so if I want to make some sort of classification on an individual, let's say, one of the steps of machine learning is doing feature engineering. So I take the raw data, and then I apply my feature engineering on that data to create these new features. And all this information of the raw data, the features I've created, it's all keyed on this individual entity, right? And so Accumulo is good for aggregating, a lot like how in the talk here, is good at aggregating all this information based on the entity. So when I do a feature extraction on the entity, so let's say I have 8 sources of logs on a certain individual. If I did this in SQL, in a database, I would have 8 tables for each data source, and then I would do this massive 8-way join, and that's a disaster. So in Accumulo instead, I can write all my data keyed on that individual because I know eventually I'm going to be grouping by on that, and I can have the data pre-group by. So if I really wanted to be aggressive too, I could write an iterator, for example, that automatically updates my feature vector, or I could just kind of calculate my feature vector on the fly based on all the data that I have about that single individual. Kind of using it, basically I'm using it as a document store in that case. I found that to be really cool because it allows me to do feature engineering on just that one group. Yeah.
If you do that over time, in other words, you get one-time shot, you write the record, and then you learn more about that individual, so you write additional information about that?
Yeah. Like you maybe your feature vector is updated. So for example, one feature I've used in a cyber use case that comes to mind for this is how many SSH logins this person has a day. So some executive is going to have 0, and that's a pretty important feature to know whether or not this person even SSHs or not. And then there's the person that SSHs 1,000 times a day, which is usually somebody that has some sort of maintenance script maybe. Then there's a guy that's doing 7 a day, So that average over time may be recalculated as a feature, if somebody's behavior changes over time, for example. So they can be updated. Or also, too, if you fold in a new data source, then you could go back and update everybody's. But that's where, if you have a lot of incremental updates, that's where adding an iterator could make sense to update that feature vector over time if you wanted to pre-compute it. The other case, like I said, is that you can just pull back all the information from the individual and then calculate the features in the client so that that code can change over time. It's not permanent. So it's more just the fact that I'm using Accumulo to group all the data together before I actually apply any logic to it. So in that case, I guess what I'm saying is that if your logic is in the client, then I can do whatever I want. I just keep it stored in that way. All right. Yeah, 5 minutes. Anybody else? Yeah. Yeah. So his question was, are you using visibility labels for A/B testing, or are you using it for not letting data through? And I have never considered using visibility labels to do A/B testing, or in this particular training set, like test set kind of separation. It's actually really interesting. I'm gonna think about that a little bit more. So basically, the idea is you could use visibility labels and say like, I'm going to assume that what we're talking about here, which is actually a really cool idea, is I could apply like a label like test set to all my data, and I could apply kind of arbitrarily, and I could apply like a label of like training set, and I could train my models on just training so that automatically it hides all the records for the test set. Then when I run over test, then I know that the data is there and I could run it. It's actually a really interesting idea. I've never really considered that. So I don't know. I think somebody should be doing that. That sounds cool. The way I've seen it used, though, on the other hand, is being careful about. There are some people that believe that you run the model over it and it's obfuscated the training data underneath, right? In the sense that I could run a model over, some sort of sensitive data and then have the output of that be less sensitive, right? And in some cases, that's not true. And so you may have models for different perspectives. Nice. So I'll wrap that up. So basically, it's more for like the ability to use the same code to train to train different models based on different points of view on the data. So if I have like somebody that has more access, they could have a model that's trained on more data. You could have a model that's trained on less data, on only the data that I can see. And that's cool. Yeah. All right. Thanks, guys.